I'm going to finish 8.1 and 8.2 stuff today. 8.1 is the easier half of that. 8.2 is similar but a little bit trickier. Those are both about solving with right triangles and solving for pieces of them. And we'll talk a little bit about 7.9 today. Like I said, you'll see the 7.9 lesson is up there. I'm still working on getting the homework edited because it's kind of a mess. They made it much more confusing sounding than it needed to be, so I have to edit a bit of it. In any case, the parts of 7.9 that we're going to deal with, we're going to have part of it is related to stuff that's on the test, but most of it is not. So when we start talking about 7.9 things, just the basics of thinking about angles and inverse trig functions outside of right triangles, that's all we're getting to in the test, or before the test. And then our test is a week from today. And we'll just finish up 7.9 and a couple other details on Thursday this week and Thursday next week also. So for today though, what I wanted to talk about was what I've got here. Just some basic ideas of, and I'm just gonna pull up my version of this, but I'll pass out paper version to you. It's sometimes kind of helpful, like I said, to just like draw on diagrams instead of trying to deal with it all on a computer screen. So I've got copies for everyone. There's just a few problems on here. I think it's 9 total. But the idea is that those relationships we talked about with respect to circles, as long as we have an angle in mind and can think of that angle in standard position, we can use the exact same relationships to talk about triangles that aren't situated on the xy axis and with the circle and all that. So like this first triangle that's up here, if I wanted to, I could certainly draw a 54-degree angle in a circle. It's a little bit more than halfway through the first quadrant, so the 54-degree angle would be maybe like that, right? And so if I wanted to finish drawing the triangle in that I see on the paper that we've got, well, let's see. The 54-degree angle here is between the hypotenuse of that triangle and a leg that's marked 12. So there are two perpendicular legs in right triangles. Those two are representative of the x and y distances here. Those are the two things that we measured that are always perpendicular to one another in triangles when we're working on coordinate planes. I don't have graph paper here. But if I want to make a right triangle and have anything about it be perpendicular relative to measurements that I was normally doing before, it'd be the x and y measurements. And this 12, notice I put it along the x-axis as opposed to this way, because if I want to have this angle in standard position, this 54 is here, and the 12 in this triangle is the length of one of the two pieces that touches that 54 degrees. The other piece is the hypotenuse. So this matches that. I've got this 12 and the hypotenuse, which length unknown, is here in the triangle. Our goal, we don't even care about how big this circle is. I don't care what the radius is. In fact, all I want to know is what's the length of this other leg? Or if I go to the right by 12 units, how far would I have to go up so that the angle formed is 54 degrees? And so I can think of it, I can reconceptualize this if I want to as a circle and then think of the same things I normally do. I don't really care about the length of this hypotenuse, so I'm not going to bother writing in the radius or trying to find the radius or whatever, but this 12 and that y are related to this 54 degrees. Thinking about the trig functions, when we talk about these coordinate points, usually we involve this hypotenuse, like r times the cosine of theta is the x value, and r times the sine of theta is the y value. But I don't really care about r. I don't need to find it. I could find r, I could find the radius of this. I could find the length of the hypotenuse, just like I could find this other side. But I don't want to. So I actually don't want to use either sine or cosine to finish dealing with this triangle, because either one of those would involve me finding the radius of the circle or the hypotenuse of this first. And this, I can do that. It's just an extra step. So the other trig relationship that we have is tangent. That's about the slope of this line, which should be definitely positive, but it'd be this length over that one, rise over run, right? So y over x. So in terms of, we talked about x equals r cosine of theta, and y equals r sine of theta. And we use those relationships when we're dealing with triangles. But if you're trying to solve, sometimes it might be helpful to have these written another way around. Like I can say x over r is cosine of theta, or y over r is sine of theta. And tangent is easier to explain this way, like with tangent by itself, because tangent's the slope, rise over run, y over x. So tangent of theta is y over x. So these are, the first two are other ways, just rearrangements of those two that we use when we set up our circular motion and circular positions. This one we didn't talk about at the time, because tangent's a different sort of function. It relates just the x and y without caring about how big the radius is at all, or the hypotenuse in terms of this triangle. So in terms of triangles, these relationships, this might have been something you talked about in an earlier class, like geometry or algebra 2, something, but cosine, in terms of just this triangle on its own, not having to worry about a radius and x and y coordinates, if I set up an angle, this is my 54-degree angle, but whatever angle I'm talking about, in a right triangle, there's always a hypotenuse and there's two sides. Whatever angle I'm talking about, when we're talking about the angles of this triangle, we know 90 degrees, so we don't have to solve for that or use it, but talking about these corresponding to x and y coordinates in these circular oriented triangles, we've always got one side that's part of the angle we're talking about, the acute angle, and so that's called adjacent to that angle, and the other side is going to be across, because there's two sides adjacent to an angle, but one of them is always the hypotenuse when we're talking about these two acute angles of a right triangle. So we've talked about adjacent to this angle, meaning it forms one of the two sides, but it isn't the hypotenuse. The hypotenuse is the hypotenuse, the one across from the right angle. And the side that isn't part of the angle, there's always one of the three sides that doesn't form the angle, it's just across from it, is usually referred to as opposite. That way you don't have to always orient your triangle like in the standard position to talk about this, but you can always redraw a picture like we did here to make it fit with our, how do I put this acute angle vertex at the origin, one side along the positive x-axis, and a hypotenuse going out to the edge of the circle. Sometimes it's a little bit confusing to do that, and it might just be easier to have other relationships or other ways to call these so you don't have to make it into a circle. So let me put these on the other side instead. But the same relationships, then this y-coordinate always ends up being the same as this length of the opposite, because of how we have this oriented here. The y distance is always going to be away from the vertex. So the y part's going to be the opposite side. I'm just going to abbreviate it that way. And the radius always corresponds to the hypotenuse. So sine, in addition to being y over r, or the y coordinate over the radius of the circle, is also the opposite over hypotenuse, just in a right triangle. Similarly, x is going to be this ratio between the adjacent side and the hypotenuse. Again, because of how we orient these in circles, the x-axis is always one of the two pieces, the initial ray of the angle. So the length along the x-axis is always part of that angle, so it's adjacent to as opposed to across the triangle from, not involved in. So I've got cosines adjacent over hypotenuse, sines opposite over hypotenuse, and tangent is just the ratio of these two legs. But since it's this slope, like rise over run, if we translate that, that's this opposite side over the adjacent side. So it's the same relationships of pieces, but when you're not working in a circle, if you just literally have triangular shapes, if you don't want to think about it as a part of a circle and rearrange it or turn it over or flip-flop, you can just think of it in terms of what's next to the angle, what's not next to the angle, and which is the hypotenuse. But realize that that isn't a completely different set of ideas. That's just translating to outside of a circle. So in any case then, dealing with this question here, I said, oh, if I want to solve for this mystery side here, it turns out that it's actually the y-coordinate that we're looking for, even though I have the letter x there, so that's another reason you don't necessarily want, like, oh, that's supposed to be the x-coordinate. It's just x as in x is unknown. But I've got adjacent and opposite sides here, not the hypotenuse. So our tangent equation is going to be useful for us. Each of these relates three pieces, an angle and two lengths, whether I write them this way or this way. There's a length, and an angle. So every trig equation that we have written here relates one angle and two measurements in length from sides of a triangle or from pieces oriented in a circle, but it's two length measurements and an angle measurement. And if we're trying to find a length and I have an angle and another length, there should be an equation that matches those three things together. It's just a matter of finding it. And in this case, tangent would be the most useful because I have the side adjacent to that 54 degrees. I want to find the side opposite to that 54 degrees, and I have 54 degrees. So it's just a matter of writing this out. Tangent of 54 is this unknown x over 12, the adjacent side. So in an exact form, just multiplying through both sides of this by 12 gets x by itself. The only thing to keep in mind that is if you wanted to compute this in a decimal format, rather than writing this, you'd need to make sure your calculator is in degree mode, or if you're doing something in iMath, you might have seen these directions. I hope you've seen these directions. To force iMath to compute a degree sine, cosine, tangent, because the degrees are much more often used when we've just got triangles than radians. It's for stationary fixed items as opposed to rotational repetition sort of things. In iMath, if you wanted to compute this and know that 54 is in degrees, it says put a D after it, so tan D, sin D, etc. That's iMath specific. That's not something that you see a lot, but most people, if they saw this, they wonder what the D's were. Oh, probably degrees. But it's not a button on a calculator. If you have a calculator, you're going to need to change the mode on it, whether that's like click on a button that says DRG or something like that until the degrees shows up. Or on a graphing calculator, it's under the mode feature, and if you scroll down a little bit, one of the options is radians versus degrees, and you'd want to put it in degrees if you're using trig functions and you've got degrees. If you're not using the sine, cosine, tangent buttons at all, it doesn't matter whether your calculator's in degree or radian mode. Doesn't make a difference. It only makes a difference for those specific functions. So in any case then, if you have, let's see, do I have this written out someplace? I think I have answers written someplace. If you do this properly, well, maybe thinking about this, all right, that angle's 54 degrees. The other one would be less than 45 degrees, 36 degrees or something, so the angles add up to 180. So the 54 degrees is the larger of the two acute angles in any case. So the side across from it should be the larger of the two non-hypotenuse sides. If you remember, and we'll talk about this called the law of sines, they're actually in proportion. It's not just kind of smaller versus bigger, but the larger an angle is, the larger the side across from it is within a right triangle. When you're on other sides of triangles, all sorts of weird things can happen. You could have long sides with, I don't know, the side lengths are still smallest to biggest, but you can have different arrangements and it's a little bit confusing. But in any case, this side across there should be something larger than 12. It should be around 16, I think. 16 and a half. So if you can get a 16 and a half-ish answer for the length of side x here, then that means you're using your calculator or calculating device properly. So what I'd like you to do is try the other two questions at the top here, and if you want to, go on to the next three. The first three are all, though, solving for unknown side lengths. Question 2 is solving for unknown angle measurements. So whether or not you have a calculator, if you have a computer, you have a calculator. If you're trying to find an online calculator and wondering about degrees or whatever, sometimes that's a bit confusing. But you should be able to at least write an equation like this or an expression for the exact answer. I'm just going to type this in here. Let me see. All right, so for the middle one here, that's actually drawn very much like an angle in standard position. I've got this angle between a horizontal and a diagonal with the right angle out to the right there. So imagine that same picture, but change that to a 58. But that means we've got, actually, to find the equivalent of the x coordinate of a point on the radius of a circle of radius 18. When we're at an angle of 58 degrees. Or we're trying to find the adjacent side to this angle when we know the hypotenuse of the triangle. So this should be a cosine function that'll relate those three pieces without having to find anything else. Cosine is the x coordinate over the radius or adjacent over hypotenuse. So cosine of 58 degrees should be x over 18. or just like the last one, to solve, it's just going to be multiply both sides by that denominator. 18 times cosine of 58 would be the exact form for our answer, r cosine of theta. This should come out to be between 9 and 10. All right, so I think it's right about 9.5 in reality. So x is about 9.5. So the third triangle here has more challenging solving, just because it's not just x over a number, get the x by itself. The x is going to end up in the denominator. It starts out as the hypotenuse of this triangle. I know the length of the side opposite from this 68-degree angle, which if I oriented it in a circle, you can imagine the 68 in that corner. The 15 is that vertical measurement. And then x would be the radius, as usual. So we're looking for the hypotenuse, or the radius. And we've got the y-coordinate, or the side opposite from this triangle. So opposite in hypotenuse, or y-coordinate and radius, that's the sine function. Or we've got sine of 68 degrees is 15 over x. So I can still multiply both sides by the denominator, but that doesn't get x by itself. It just gets it out of the denominator. So you can do that, and then to get x by itself, divide by sine of 68. Or if you remember the trick you might have talked about if you had a bunch of questions about solving proportions long ago, you can flip-flop the things on the diagonal because it's just skipping a step. Like x times sine of 68 equals 15. To get the x by itself, divide by that. Or in other words, we end up with x equals 15 over the sine of 68. So that'd be the exact form. Sine of 68 equals 15 over x. So x equals 15 over sine of 68. Which should be a little over 16, 16.2. All right, so there's only a few different ways that just having triangle information given, you can solve for sides. There's not a whole lot of mystery. These three, this one example of a sine, a cosine, and a tangent, like pieces of given information. Just, you have to have 2 out of 3 pieces of the parts to a trig function to solve this way. So that's 2 sides and an angle. You need to know 2 out of 3. Each of these was knowing 1 angle and 1 side listed. I mean, obviously we could find the other angle also, in order to find the remaining side. Now, if you know 2 sides and don't know any angles other than the 90-degree angle, we have to solve a different way, because the unknown is going to be inside the trig function. Unknown is going to be the angle in these cases. But setting up the original equations is maybe easier when you have these, because you can see the pairs with numbers listed. It's like, oh, I'm going to look at these 2 numbers like this. These 2 are perpendicular to one another. That'd be like a y and an x coordinate. If I arrange this into a circle, and in fact this is set up, drawn in standard position with one side of the angle we're interested in along the horizontal, and the other one up diagonally from that. So I can imagine that being let's see, what was it? 21 across and 13 up. Or, in other words, I've got a coordinate point 21, 13 here. Don't know what the radius is. I don't have to find it. I could certainly, Pythagorean theorem or something. What I'm interested in is, how big is this angle? So I just marked it as question marks, so it's easier to type into these. But that combination of known pieces, the x and the y coordinates, goes easiest with tangent. I mean, we could obviously solve for the third side and do the other functions as well, but tangent, opposite over adjacent, or y over x is the most direct, don't have to solve for any extra pieces, way to set up an equation here. Meaning, I'm just gonna say, okay, tangent of, here I'll just write it as question mark again, still easier to type. Opposite over adjacent, or y over x, is 13 over 21. Oops, 13 over 21. Now, the only thing is, if I want to solve for this angle, I have to get rid of tangent. I have to untangent this, which means I'm going to use an inverse function, inverse tangent. I'm going to take inverse tangent of both sides, which essentially undoes what I have on the left. And inverse tangent, we talked about this. There's two different notations for that. The easiest one to type is arctangent. Oops, 13 out of 21. The other notation involves the inverse on that, like -1 exponent, like inverse functions. So arctangent of something means the same thing as inverse tangent, tangent with a -1. Those are two different notations you'll see written in books that mean the same thing. Now, again, in terms of iMath, if you want it to tell you an answer in degrees, you have to throw a d in there. You can do arctangent d to make it give your answer out in degrees, because the input to these inverse functions is that ratio, and the output is the angle. So on your calculator, if you're in radian mode, it'll give you your angle answer in radians. If you're in degree mode, it'll give you your angle answer in degrees. If you're in iMath, it's like, well, you have to tell it how you want your answer. If you just write it as regular arctangent, iMath's default is radians. If you want it to come out in degrees, throw an extra d in there, and that'll make the answer come out in degrees. Although, if you have an answer that's in radians and you want to convert it to degrees, we should know how to do that also. Back to section 7.1, think about that. You've got a test coming up in a week. But in any case, arctangent of 13 over 21 would help us solve the first one. It should come out to be a little under 32 degrees. Let's see, where did I write this anywhere? Oh, right here. 31.8 is what I had. So if you can get 31.8-ish, that should mean that you're doing this approximately correctly. Try the second and the third ones here, and see if you can get results for those. I'll give you a little chance to practice setting them up. Think about which of the three available trig functions most easily relates the parts that you do have. Although you're free to use whatever, you should get the same result as long as you up to round off error. But let me put this in. 31.8. first quadrant, because their diagrams aren't going to be too far off from one another. But just if you want to make it look kind of to scale, you can vary the size of the angle and see, oh, well, let's see, if I put that question mark angle at the origin, at 48 would be the radius, and this side is across from that. That'd be like the y coordinate, the opposite. So I've got the y coordinate and the radius, or the opposite and the hypotenuse. And so the easiest way to relate those is which of our three trig functions? Sine, cosine, tangent? Sine, right. So the sine of our mystery angle should be 25 over 48. So if I want to solve for mystery angle, sine of, let's see, question mark, is 25 over 48. So just like before, we're just going to do inverse sine. So our question mark mystery angle is arc sine D if you're on iMath, of 25 over 48. And that will give you some acute angle or other, and should be smallish, relatively speaking, but about the same size as the last one in reality, 31 point something else, 31.4. And the last question here, again, if you imagine that angle in at the x-axis, or at the origin, and the hypotenuse is the radius, so just imagine maybe flip this up, flip this over that side that's length 48, and it would be in that standard position. So I've got a radius of 57, an x coordinate, or an x distance of 48. So I've got the ingredients for a cosine function, adjacent and hypotenuse, or x and r. So cosine of our mystery angle, 48 over 57. And so our angle in exact form would be arc cosine, and make sure you type 2 C's in that if you're typing it in iMath for anything, or arc cosine D of 48 over 57, which should be, again, 30 something degrees. This one's slightly bigger, 32 point something. 32.6 is what I had. Does that sound right? All right. So in any case, there's only so many ways that these could be set up for you. We're only dealing with right triangles. In order to use trig to solve, you either need two sides or you need an angle and a side. If you have two angles and you don't have any side lengths, you can't solve for side lengths. That might sound like a geometry thing, because if you don't know any side lengths, you don't know how big your triangle is. It can have the same angles and be any size, like magnification, although they will be similar. So in any case, on the back side of this are story problems involving triangular things. Keep in mind when you see, so test-wise, most of the questions on the test have diagrams that go with them, or graphs that go with them. A few do not. If there's things described that are visual sorts of things, like coordinate points, or a ladder leaning against a building, or whatever it is, draw a diagram for yourself. Even if there isn't one there, it can help you picture how all the pieces or all the details go together. And keep in mind that this entire test, it's not a final exam covering everything, it's just on trig stuff. So everything is going to involve angles and triangles and circles and the stuff that we've been dealing with. So if I've got a 5 meter long ladder leaning against a building, and I've got an angle between the ground and the ladder, and how far is this diagram time? So you know how all these pieces are related. Don't try to do it like pictured in your head and not draw anything. Otherwise you're bound to get the numbers or the positions of the angles relative to one another mixed up. I mean, you can do it if you want to, but I would suggest to draw a diagram. And if I have a 5 meter long ladder leaning against a building, doesn't say so, but we'll assume the building is standing upright. And I've got a ladder leaning against it. And the ladder's 5 meters long. I don't really care how tall the building is. I could wonder, where does the ladder hit the wall, but it doesn't matter. What we're asked is, let's see, if the angle between the ground and the ladder, so ground, 57 degrees, which I believe we had a 58, we've had 54 degrees, we've had 58 degrees, so 57 is going to be pretty similar to the triangles that were the first and second questions we dealt with, just different size. I want to know how far from the wall is the bottom of the ladder. Oh, well, that's that distance. So assuming that the building is upright, meaning we've got a 90-degree angle between the ground and the building, that should be enough information for us to solve. And magic, we've got an angle in standard position even. So we have this radius of 5, an x-coordinate, or a horizontal distance, is what we're looking for to solve, and we've got this angle in standard position of 57 degrees. So trig function that we could use for this, with this adjacent and hypotenuse, or x-coordinate, or horizontal distance and radius, it's going to be our cosine. So, and this is the easier sort of one to solve because the radius or the hypotenuse goes on the bottom. Cosine of 57 is just our question mark, unknown side, over 5. So we just need to find 5 times cosine of 57 degrees, and we'd have our answer on this one. And so it's very similar to the second question on the top. Or on the front page, I should say. So take a couple minutes. The second and third questions on here use this phrase, angle of elevation, which is a fairly common phrase in trig story problems, but just in describing angles as they appear in reality, angle between something, if you're looking like, oh, that's so many degrees up, oh, that's the angle of elevation. An angle of elevation is the angle up from the horizontal, or above the horizontal, or angle in standard position. So take a look at these last 2 questions, see if you can visualize what's going on, set up a triangle, and solve. So this is like 2 point something, I believe. I don't remember that number. I didn't write it down. Something less than 2.5. .7. Oh, that's right. Oh yeah. Sorry, finding this line. That one's more than 2.5. This one's less than 2.5. so angle of elevation. So at a point 30 feet away from the base of a tree, the angle of elevation, the angle up from the horizontal toward the top of the tree. So this angle of elevation is always going to be measured between the horizontal and something above the horizontal. So it's from horizontal upward, so just like standard position angle. There's also a phrase that you'll see every once in a while, is angle of depression. It's the same thing, but measured down from the horizontal. So an angle of depression. So like if you're thinking about like, oh, you're up on the top of a large hill and looking down to something, or if you're flying over in an airplane and looking down to something, or in a lighthouse, I think is one of the examples I've seen, like looking from a high position down to something and measuring that angle down from the horizontal, that's an angle of depression. But angles of elevation are pretty common for, people looking around and like looking up at something. It's easier to walk around and do that than walk around and look down. It happens in just more general situations, I guess. But in any case, angle of elevation is that angle there, and it says that this is 52 degrees. And we want to know the height of the tree. So, I can call it y, for, it's the vertical part in this picture if you want. X is 30, y is the unknown, and we've got an angle of 52. We don't care about this length here because what even is that? The length of the distance from where you are, straight line to the top of the tree? Well, I guess if you wanted to have a rope that went up there, maybe you'd care about that, but we don't need that length, the hypotenuse or the radius of a circle, if we drew a circle for any reason. So tangent should help us out here. Tangent of our angle should be our y over x, or tangent of 52 degrees is our unknown over 30. So from there, just multiply by 30, and make sure if you're using iMath, you call it tan d of 52, so it knows that the 52 is degrees and not radians. But 30 tangent of 52 degrees would give us that height. And let's see. It should be like 40-ish or something. I think it's just a little bit under 40. But let's see here. Tangent of 52 is 1.27 times 30. Yeah, 38-ish. And that would be feet. It's a distance, so it's not 38 degrees. A lot of these questions, when it's like a large scale, something like this, will just ask the nearest whole number. Some will ask to 2 or 3 decimal places just to make sure you're using your calculator right. But in reality, the chances of you knowing this angle to at a close enough measurement to be able to say the number of feet to a few decimal places is rare. So lots of times we'll just say round to the nearest whole number, or to the nearest, if it's in thousands or something, round to the nearest 1,000 or 100 or something like that. So last question on here, and then I want to talk about the other issue with these inverse trig functions, because we're going to need one for this last question. An observer is 120 feet from the base of a radio tower, which is 150 feet tall, and we're going to try to solve for the angle of elevation. So 120 feet, not to scale here, from the base of something that's 150 feet tall, and I want to know the angle of elevation, or the angle up from the horizontal. So we're going to have to use inverse tangent for this. Inverse tangent of opposite over adjacent, or y over x, rise over run. Right, so tangent of theta is 150 over 120, meaning inverse tangent of 150 over 120 is how we find theta. And I don't know what that is off the top of my head, but it's more than 45 degrees. So So the reason I'm saying that, just having a good sense of like, should it be bigger or smaller than something's like, all right, if this were a 45-degree angle, the x and y coordinates would be the same. So the horizontal and vertical would be the same if this was a 45-degree angle, that halfway through the first quadrant. So I know this one's bigger, that means I'm past 45, I've gone up farther around the circle. So just in terms of like, does my answer make any sense? Take them, especially with these applications, take a minute to think about that. It's easier on these sometimes than on the random triangles drawn every which way. But let's see, 150 over 120 is 1.25, and I want inverse tangent of that. Now, let's see. There we go, 51.3 degrees. So about 51 degrees. Or, in other words, it's pretty similar to the previous question on trig, which was 52 degrees. So, I want to talk about these inverse trig functions. Thinking of circles and angles, I'm going to post a document about this after class on, or maybe before class on. Before class on Thursday sometime. But just in terms of all of our trig values, when we're not just talking about triangles, where the lengths are all positive and all these fit in the first quadrant, you can have negatives and there's repetitions of these same values. You know, our trig values, they have a period of 2 pi, but they go through all their values a couple of times between 0 and 2 pi for sine and cosine. So, thinking about, like, if I have, let's see, here, let me make this definitely less than 45 so it's not like confusing. All right, so let's say that this is about 0.8 comma 0.6. And why I chose that is because that makes a radius of 1, which means our sine and cosine are the same as our y and x. 0.64 and 0.36 add to 1. So this triangle should be larger. Sorry, I drew it the wrong way. I was trying to make it there. No. It was probably right in the first place, but in any case. 0.8 this direction, 0.6 that direction. In any case, there are, if I say that this then, since my radius is 1, this is my cosine of theta, and this is my sine of theta. Like, there's another point on this circle that also has a y value of 0.6, right? It's over here. So if I just use, sine of theta is 0.6, solve for theta, I'm only ever going to get this angle. I'm going to get an acute angle, and my calculator's never going to give me the other one. The reason is inverse sine is a function. It only has one output for every input. So it's not going to give you a whole variety of every single angle that has that same sine value. There's infinitely many of them. There's not just 2. There's 2 between 0 and 2 pi that have the same sine value. And then there's another 2 if I were to go around the circle again and again and again and again. So how are we supposed to deal with that in terms of like, well, what if I don't just want to get a first quadrant sort of acute angle answer? What if I want to solve for something else? Well, we're not going to solve for it using inverse trig functions. We're just going to use symmetry to solve for it. So saying, well, if this angle, like let's say this is 50 degrees, because it kind of looks like it in this picture. If this angle is 50 degrees, I'll just use degrees because it's easier to deal with than like weird multiples of pi or something. But if this angle is 60 to 50 degrees, that means it's 50 degrees above the x-axis. It's also 0.6 units vertically above the x-axis where this terminal ray hits the edge of the circle. So the same thing I could say over here, even though it's not in standard position. If I were to draw this ray is 0.6 units above the x-axis, because this angle here is the same as that. It's also 50 degrees above the x-axis. That's not how we measure angles in standard position. But if I know that this line is 50 degrees above or 50 degrees less than being 180, I know precisely how big it is, be 130, right? If I were to measure it the right way. If I know how big this angle is, like if I solved and got that this was 50, I didn't solve, I just made up a number. But if I solved and got that this was 50, then I know where this is in angle measurements, not starting from 0, but I know, oh, it's 50 degrees short of the x-axis. Or similarly, if I were dealing with maybe a line down here where it has the same cosine value. This is 0.8 comma, well, it'd be negative 0.6, but the 0.8 part's the same. Or I know this is kind of the same position, just in a different quadrant. In order to have similar, but maybe just like positive and negative sign different coordinate points, I'm in these symmetric sort of positions, like reflections across the axes from one another, which means angle-wise, all of these 4 diagonal lines that I've drawn are all 50 degrees away from the x-axis. And I could find a degree measurement for all of them, like measured the normal way, as opposed to saying 50 degrees away from the x-axis. But 50 degrees away from the x-axis relates to these numbers. Well, you know, either one of them. I could have solved, like, cosine of theta is 0.8 and gotten a result for that. But cosine of this angle is also 0.8. And I'm never going to get 200 and something degrees, or 300 and something degrees, from inverse cosine, just like I'm never going to get 100 and something degrees from inverse sine. So the idea is, if you have these angles in these other quadrants and you're trying to figure out what is their degree measurement, when all you have are these positions and you're trying to use inverse sine, cosine, tangent, you're not always going to be lucky enough to have it in the right one. Because all the values repeat, and these inverse trig functions only give you outputs in certain quadrants, and some of them give you negative angles. We'll get into the negative angles after your test. But just keeping in mind, since the sine of an angle is related to the y-coordinate over the radius of a circle, and radius is always positive. Sine is positive wherever y is positive. So here, let me just draw quadrants. So sine is positive, I'm just going to write like that, in the first quadrant and the second quadrant. But inverse sine of a positive number will only ever give you the first quadrant answer. Sine's going to be negative down here. I don't even want to do inverse sine of negative numbers. We don't need to. If you're trying to solve for an angle, and this is what we're going to talk about more on Thursday and then after your test, if you're trying to solve for an angle using inverse trig functions, don't bother with doing inverse sine of a negative something. Just do an inverse sine, cosine, tangent, inverse trig of a negative anything. Just do an inverse trig of a positive something. You'll know for sure then you're always going to get, just like what we did when we were dealing with triangles, you'll get a nice acute angle, and we can just use symmetry to translate that where we want. Because it's not that it's unpredictable, it's predictable, but it's just different for every trig function what an inverse is going to give you. So if you do an inverse sine of a negative number, it's going to give you a fourth quadrant type angle, but listed as like negative 30 degrees, negative 40 degrees, like it's not pleasant. That's not what you generally want. Even if you wanted it in the fourth quadrant, you probably want it in a positive, like 300 and something degree sense, or in radians, whatever measurement. So similarly, cosine, since it's the x-coordinate or the horizontal distance over the radius, and the radius is always positive, this is going to be positive whenever x is positive. So cosine is going to be positive in the first quadrant, and the fourth quadrant. And negative over here, right? I'm just writing in the positives, so negatives elsewhere. Tangent doesn't involve the radius, it involves y and x. It's that slope. Well, you know, slope's positive if you're going like up and to the right. So that's first quadrant and third quadrant. We've got positive tangents. Second quadrant and fourth quadrant be where lines with negative slopes that go through the origin would go. So tangent's going to be positive in the first quadrant and also the third quadrant. So inverse tangent of a positive number is always going to give you a first quadrant angle, even if you really want the third quadrant one, or something that's spin around 7 times and then stop here. It always just gives you an acute angle if you do inverse tangent of a positive. And if you do inverse tangent of a negative, like sine, it's going to give you a fourth quadrant-ish angle, but label it as negative something, like a negative acute angle. Inverse cosine of negatives gives you second quadrant angles, which are not easy to deal with if you didn't want a second quadrant angle in the first place. So the reason I'm talking about all of this is if you're trying to solve for an angle and you like know visually where it's supposed to be, regardless of where it's supposed to be, I would highly suggest just do inverse sine, cosine, or tangent of a positive number. Like if you have a negative, just get rid of the negative sign. Just kind of like if you're squaring a number, don't square the negative, just pretend it wasn't there in the first place. Only a little bit harder because you actually have to then convert it into a different quadrant where it's supposed to be. But by doing inverse trig values of first quadrant angles, what you get is the number of degrees or radians away from the x-axis that any angle with a positive or negative, any angle with that same absolute value of its trig ratio is going to be. So if I got inverse sine of some angle was, or inverse sine of some ratio gave me an angle of like, let's say in degrees, 70 degrees. Like, oh, well 70 degrees could be 70 degrees up from the x-axis or down from the x-axis. All those would have the same up to plus or minus signs, trig values. If I'm up 70 degrees here, up 70 degrees there, which would be 110. Down 70 degrees there, which would be, let's see, 180 plus 70, 250, or short of 360 by 70, which would be 290. Same works in radians. You're just gonna, instead of comparing to like 360 and 180, you'd be comparing to pi and 2 pi. So I'll post a document about that, kind of like with more visuals about that, but the idea, again, is that if you're trying to solve for angles that aren't as a part of a right triangle, you might be dealing with obtuse angles, and you might not get them by using inverse trig functions. By using inverse trig functions of positive numbers, you can guarantee yourself that you're going to get a first quadrant sized angle, because that's how these functions have been defined, these inverse trig functions, to have like function idea, one output for every input. So sine and tangent inverse functions, their range, not their domain, is negative pi over 2 through pi over 2. Let's see, I'll just put these parentheses. Meaning the output from any of these in radians is going to be between negative x, like the negative y-axis, but going there backward, and positive y-axis. So in other words, this is like negative 90 degrees through 90 degrees. Cosine, in order to cover some positives and some negatives, inverse cosine's range is like 0 to 180, 0 to pi. Zeros always come out, the pi over 2s and other 90s don't. So tangent is actually undefined at negative 90 and 90, like vertical lines, that's that undefined slope. Sine is defined there, but not worrying about the endpoint specifically. the ranges of these or the outputs of these are just one quadrant where it's positive and one quadrant where it's negative in all of these cases. But rather than worrying about that, you say, all right, I don't really care where this function's outputs are going to exist. I'm just going to deal with this first quadrant where all of the trig functions have positive values. So inverse trig of a positive number will always give me a first quadrant angle as a result. And that's predictable, and it's easy then to convert it into other quadrants using what are known as, well, sometimes they're called coterminal angles because they have the same terminal ray, but they're also called reference angles, meaning, like I'm using this 50 degrees as a reference because it's got the same general distance away from the x-axis and y-axis in all those spots, but our angles are measured in the first quadrant relative to the x-axis. So that's why I use that, how far it is from the x-axis as opposed to the y. All right, so I'll stop at that for today. I'm going to post both the worksheet with story problems we did today and what I was just talking about related to inverse